Hey everyone, and welcome to today's Explainer. We are going to completely demystify one of the most widely used programming languages on the planet, Java. We're not just staring at syntax today, no way. We're getting right under the hood to look at Java's core characteristics, how it actually listens to our physical actions, and, maybe most importantly, its built-in fail-safes for when things inevitably go sideways. So whether you're writing your very first lines of code or you're just looking for a deeper understanding of how software handles human error, you are in exactly the right place. Let's get into it.
Okay, let's dive right into this. Here's our quick 4-step roadmap for today. First, the power of Java. Second, interactive mouse events. Third, when code goes wrong. And finally, catching the exceptions.
Starting off with part 1, the power of Java. We'll be exploring its fundamental characteristics. You know, it's absolutely crucial to realize that Java isn't just a random pile of coding commands. It's a seriously robust solution designed from the ground up to solve complex problems across all sorts of systems. Take a look at these core traits. First off, it's built to be simple, especially compared to older languages like C++. It does this through automatic memory allocation. Basically, there's a built-in garbage collector that automatically cleans up memory leaks for you. Super handy, right? It's also object-oriented, which just means developers can easily reuse code and create distinct objects to manipulate data. But I gotta say, its real superpower, being architectural neutral. Thanks to the JVM, the Java Virtual Machine, you write your code once and you can run it anywhere without having to recompile it for different operating systems. And even with all that flexibility, it still rocks high performance because it uses just-in-time compilation. Think of it like a live translator, converting code into machine language on the fly exactly as the program runs.
Now notice that satellite network on the left side of your screen. That perfectly illustrates how Java is a distributed language. It has networking capabilities seamlessly baked right in, which makes distributed computing across different machines an absolute breeze. And then, looking at that macro circuit board on the right, we're seeing Java's immense hardware portability. Because it's architecture neutral, the Java environment is portable to totally new hardware and software setups without constantly needing to be recompiled. It essentially acts as a universal translator across the entire digital world.
Moving on to part 2, interactive mouse events. We're looking at making Java actually listen.
So we've got this powerful, high-performance platform, independent engine, right? But an engine isn't much use if we can't drive it. In Java, listening to our physical actions is cleanly divided into specific interfaces. On one hand, we have the mouse listener. Think of this as your digital tripwire for specific, distinct actions. It handles the exact moments when a mouse is clicked, pressed, released, or when the cursor enters or exits a specific area. Now contrast that with the mouse motion listener on the right. This one handles the ongoing physical journey of the mouse. It's specifically tracking when the mouse is just moving across the screen or when it's actively dragging something along.
And hey, speaking of dragging, let's actually ground that technical concept with a very specific physical definition. In the Java environment, dragging isn't just casually moving the cursor around. No, it's explicitly defined as moving the mouse while the mouse button is actively being pressed down. By strictly defining this physical interaction, Java knows exactly when it needs to trigger a mouse-dragged event versus just a simple mouse-moved event.
All right, part 3, when code goes wrong. We are diving into the inevitable human error.
Now what's really interesting about this slide is the core question it asks: why do we need to handle exceptions? We know Java can listen perfectly to our physical commands, but what happens when the human giving those commands makes a massive mistake? In programming, an exception is basically just an unwanted event that completely disrupts the normal flow of our program. To really answer this question, we have to look at what happens when a program assumes a user is going to behave perfectly, and then the user absolutely doesn't. Let's walk through a little micro-story from our source material. We'll call it the Sample Run 2 disaster. Imagine a perfectly innocent user sitting at their desk. The program asks them to enter a dividend, and they confidently type 24. Great. Then it asks for a divisor. The user, maybe not really thinking about the fundamental laws of mathematics, types in a 0. The program, completely lacking any built-in foresight, just accepts that 0 and attempts to divide 24 by 0 without checking the input first. And the result? The entire program immediately terminates and crashes. Boom. Done.
And when it crashes, this is the exact, frankly intimidating output the system spits back at the developer. Exception in thread main java.lang.arithmetic exception /by 0. Because the program didn't bother to check if the divisor was 0 before attempting the math, the system hit an impossible logical wall. It literally threw an arithmetic exception and just gave up completely.
And division by zero is definitely not the only way a user can break your code. The sources also highlight sample run 3. Imagine the program asks for an integer, a whole number, and the user slips up, hits the keyboard, and types 2e instead. Under the hood, Java relies on strict basic elements, like tokens and identifiers, to understand vocabulary. Letters simply cannot be expressed as integer values. It fundamentally breaks this basic vocabulary. Because the next int method doesn't have a clue what to do with a letter when it expects a number, it throws an input mismatch exception, and once again, the program abruptly terminates.
Which brings us to part 4, catching the exceptions, building software failsafes. So the crucial point here is how we fix this. The reality is, we can't control what a user types, but we can absolutely control how our program reacts to it. Rather than crashing, we can perform an appropriate action. And this brilliantly illustrates exactly how we fix that division disaster. Instead of blindly trusting the input, we use basic logic to create a safe path. Step 1, we write a simple if statement. If the divisor is not equal to 0, awesome, go ahead and do the math. Step 2, else, meaning if the divisor is 0, don't do the math. Just print a polite message saying, cannot divide by 0. By adding this one simple check, the program handles the exception gracefully, prints a warning, and just keeps running instead of crashing. It's a total game changer.
Now, to manage all these potential disasters, Java categorizes them into a strict hierarchy. At the very base level, everything is a throwable. From there, it splits into 2 main branches. First, you have errors, like a linkage error or a virtual machine error. Honestly, these are catastrophic, deep system failures that your program usually can't recover from. But the second branch is exceptions. This includes things like class not found exception, I/O exception, and that runtime exception we just dealt with. These are the issues your program can, and absolutely should, anticipate and handle using try-catch blocks or logical checks.
As we wrap up this explainer, I want to leave you with a final thought to really chew on. We just saw how a tiny, simple block of logic prevents a basic calculator program from completely crashing, right? But remember, Java is the architecture-neutral distributed engine powering everything from global satellite networks to massive enterprise financial systems. If failing to check for a single 0 crashes a tiny program, what kind of massive real-world disasters could a beautifully written failsafe prevent in a global banking system or, say, a life-saving medical device? Understanding these core foundations isn't just about passing a coding test. It is about building a safer digital world for all of us. Thank you so much for joining me on this explainer, and keep questioning the code.